Okay, thank you. So yeah, Wonkari, please go. Stage is yours.
Oh, okay. Sorry for the time consuming. Hello everyone. I'm Wei Wang, a postdoc at Shandong University. Collaborate with Professor Jian Yang. It's my great honor to be here to share our results on RNA structure modeling as a server group. Our group Yang server is mainly powered by modeling template-based modeling. Firstly, let me introduce the method details. About 2 years ago, we developed the TR within RNA, a deep learning-based method to predict the RNA 3D structures. With this method, we achieved a commendable ranking in CASP15. The corresponding web server has handled over 13,000 tests, demonstrating the wide application of our method. TR-RNA adopts a two-step approach that is firstly predict the geometric residence using neural network, and then fold the 3D structure using energy minimization. After CASP15, we keep improving our method and developed an end-to-end approach, TR-RNA2. The inputs are still the MSA and the secondary structure, which are referred as SS here, and they are updated by they are processed into two representations and updated by a transformer network RNA former. The main difference is that we now use a SS-aware structure module to directly predict the 4-atom structures through neural network. In other words, it enables end-to-end prediction from the sequence to structure. This 4-atom end-to-end training significantly improves our performance. Meanwhile, the energy minimization based on the predicted 2D geometries is still applicable, which is useful when the end-to-end model has serious structural violations. We use TR-RNA2, referred to as TR-RNA2 here, to participate in the CASP16 experiment. Starting with the RNA sequence, we use Inferno to search the RNA central database and generate an MSA. It is worth noting that we prepare multiple 2D structures using both predictive and template-based methods, which will be shown in the next page. This can improve the diversity of our predictions. Considering the 2D structure can sometimes be inaccurate, especially for some challenging targets, we also generate a null asset prediction using TR-RNA2. In addition, considering some templates may exist, we also use RNA Threader. It's a template-based method from our lab to identify 3D template and generate the decoys based on it. Finally, we apply a 2A module to select the top 5 modules for submission. For large oligomers, the decoys are generated using the AF3 as these targets are beyond our current capability. To prepare the input 2D structures, we use predictive methods, including our in-house module named TR-RNA-SS, which uses the RNA former module to predict the 2D structure, along with other methods, including the spot RNA and the ET-RNA fold. For the template-based approach, we use the RNA Threader from our lab and R2DT to find the 2D templates. Overall, for each target, we generate about more than 5 2D structures. Now I will introduce the results. This page compares TR-RNA2 with its predecessor TR-RNA using two benchmark datasets that do not overlap with our training set. The results show that TR-RNA2 significantly outperforms TR-RNA across all metrics, including global metrics like RMSD and TM score. as well as the neutral methods such as LDT and INF. The head-to-head comparison also confirms that TRA2 shows improvement on most targets. In CASP16, we used the Young Mortimer group to perform a blind benchmark test, comparing TRA2 with other leading deep learning methods. Specifically, we submitted predictions from TRA2, TRA, rotated fold NA, deep fold RNA, and raw fold as modules 1 through 5 respectively, all using the same inputs. We also ran the recently published raw fold plus on these targets. The results show that TRA2 outperforms all the compared methods in terms of these various methods. In addition, our modules also have far fewer stereo classes than other methods, with an average class score of only 2. According to the official ranking, our group Young server is ranking at the best server group, and surpassed only by 3 human groups, and is better than the AF3 server. Since our results for the large oligomers come from AF3, we focus on the remaining targets, for which the predictions are from TRA2. On these targets, the ranking doesn't change much. This confirms that our method does outperform AF3 for these targets by exploring a diverse set of references from 2D structures to templates. Now let's look at some examples. The first one is R1288, for which our modules is the second best overall, while the AF3 module only achieves an average level. For this target, TRA2 is competitive with the best AF3 module when asset is not used. The performance improves further when the predicted asset is introduced, and this improvement is captured by our QA module. Additionally, our modules have far fewer classes compared to others. This demonstrates that our prediction is commendable in both accuracy and the statistical validity. For another example, R1256, which has 30 confirmations, we can also observe similar comparisons. For this target, our modules achieve the best accuracy over all submissions, while the AF3 server is still not competitive. Similarly, TRA2 is competitive with AF3 without SS input, and shows significant improvement when the predicted asset is used. And this can also be captured by the QA module. And the class through our modules or our modules is much lower than AF3 module. The next example is R1281, where our group also achieves the best performance. In contrast, AF3 server performs below average with a z-score of 0. For this target, we can identify the 3D templates using the RNA threader method. We then achieve a reasonable performance either by running TRN2 with the SS from the template or by directly using RNA threader to do template-based modeling. These two modules are both better than the F3 module. This example illustrates that the template information is valuable, especially for the large RNA modeling. However, there are some targets where Young server performs poorly. For example, for R1255, although TRA2 generates an accurate module with the default input, in other words, using the TRA-SS as the input, this module is not included by our QA program in the top 5 modules, leading to the much worse results of Young server compared to Young Mortimer. This reflects that the robustness of quality assessment method for RNA still needs improvement. In addition, our method performs poorly on some RNA chains derived from protein RNA complexes, as we didn't consider the protein information. However, we also observe that AF3 predictions are not improved by the inclusion of the protein partner for this RNA target, named R1212. This shows that how to use the protein partner information to improve the RNA modeling remains an unsolved problem. Now let me briefly summarize our talk. We developed an end-to-end modeling method, TR-RNA2, which outperforms its predecessor, TR-RNA, and also outperforms AF3 on the not too large targets by incorporating diverse assets and template reference. This helps us achieve strong results in CASP16 as an automated server group, and the ranking has been improved compared to the young server in CASP15. However, we acknowledge that there are still many challenges in automated RNA structure modeling. For example, for large RNAs with over 500 NT and oligomers with more than 2 chains, the current automated method still struggles, especially when the templates are unavailable. Additionally, the accurate prediction of protein RNA complexes remains challenging, and how to use the protein partner information to enhance the RNA modeling is still unsolved. But we believe that the automated modeling will get close to the even surpass the human experts with more advanced AI methods developed in the future, and more RNA data being served in the PDB database. Finally, I would like to thank the organizations and assessors and my supervisor, Jin Yang, and the support from NSFC. That's all. Thank you.